Well, hi, everybody, and welcome to Open Hardware TV. This is Season 3, Episode 5, and today we're talking about the verification of the CORE-V-MCU, its past, its present, and its future. My name is Mike Thompson. I am the Director of Engineering for the Verification Task Group, and I'm joined today by Tim Sachs, who is the CEO of QuickLogic, and David Poulin, the CEO of Datum Technology. And each of these fine people have agreed to present for us today and talk about the aspects of verification that their organization are involved in with the CORE-V-MCU. As we've done with all other open hardware presentations on Open Hardware TV, the content from each of us is pre-recorded, so we will quickly switch over to the pre-recorded content, but we will be watching with you, and we will take questions live at the end of the presentations about 30 minutes from now. So with that, sit back and enjoy, and we will see you on the other side.
Well, thanks, Mike. Thanks for that nice introduction. And if I might say, you're doing an excellent job of moderating this episode of Open Hardware TV. So what I'll be talking about today is CORE-V-MCU verification. We're going to reintroduce the CORE-V-MCU project. Some of you will remember an Open Hardware TV episode from Season 1 where we talked about the MCU in a fair bit of detail, and then there was a subsequent episode where we talked about the software that will be produced for the MCU. We're going to take a little step back and talk about the verification. So we're going to talk about the verification that's employed for this SoC. Also going to take a little bit of a detour and get you started on the CORE-V-MCU FPGA prototype platform. You can actually start working with this today. And then we'll wrap up with an introduction of the CORE-V-MCU-UVM project, which is a project that we'll be deploying to fully verify this SoC to the same level of quality as we've done for our RISC-V cores. So just a quick reintroduction of the CORE-V-MCU. This will be old information for those of you who are familiar with it and maybe new for some of you. This is a full-on system on chip. It's based on the Pulp Platform's Pulpissimo device that was developed by ETH Zurich. It was at the time based on a core called RISC-V. RISC-V has been absorbed by the Open Hardware Group and has been rebranded as the CV32E40P. And you'll see here on the MCU, the block diagram on your right, the CV32E40P is instantiated there. This device, this IP has been verified to a very, very high quality. It is fully able to be used in an industrial setting. This thing comes with full-on DV plans, coverage, user manuals, and open source implementation of both the test bench and the RTL. Another thing you'll notice here is the embedded eFPGA from QuickLogic. Tim Sachs will be talking a little bit more about that later. This is an embedded FPGA that is fully programmed using open source tools. In addition to those great things, we've also, we've got the traditional things that you would see in an SoC, an interconnect to connect the core and the FPGA to memory blocks and to an embedded micro DMA engine that allows you to drive IP blocks to external I/O, things like a camera interface, a SPI interface, I2C, UART, all of that good stuff. I want to talk a bit about technical readiness levels and the technical readiness level scale. Some of you may have seen this before. This is something that was developed by NASA in the 1960s, which is going back a fair piece. It's since been adopted by a wide variety of institutions, including governmental and industrial organizations. The TRL is a way of communicating basically what level of documentation, what level of implementation, and what level of verification has been done for a particular design or piece of IP. You may recall last year we made a very big deal out of taking our first CORE-V RISC-V processor to TRL5. TRL5 is where you can take a device and take the IP, integrate it into your SoC or ASIC or FPGA, and be very confident that this thing will work fully as intended without any bugs. We deliberately chose not to take the first iteration of the CORE-V-MCU to TRL level 5. Did that basically for time constraints. We want to make the SoC available to the community so that hardware developers, firmware developers, and software developers can engage with this thing as quickly as possible. So what we've done here, we're releasing the first silicon to something called TRL3. This is a proof of concept. This will work for you. This will enable you to start working with the device. But what we really want to do is we want to take the IP that's in the CORE-V SoC and upgrade it to get it to the same level of technical readiness that we have for the core itself. So we want to go from here to here. I mentioned earlier that you can start working with this now. If you go to Digilent and get yourself one of these Nexus A7 FPGA development platforms, you can download the CORE-V-MCU to this FPGA, download software to the MCU, and start running programs today. Start using it with a integrated development environment. This is all available to run today. How do you do that, I ask, or you ask? Well, go to this repository on GitHub, core-5.mcu, and scroll down, look for the Quick Start Guide. Quick Start Guide will get you all the information you need, which hardware you need, which open source software you need, how do you get it up and running, and you can be using the CORE-V-MCU basically right now. So how did we get to this stage? Well, you know, like everything, it takes a little bit of verification to get going. If you want to have something that makes it useful for the general population and the community to use, it takes quite a bit of verification. So to get us to TRL level 3, we have rolled out something called cli-test. CLI means command line interface. This is a standalone processor-driven testing platform for the CORE-V-MCU. Essentially, it's a library of C tasks that run under FreeRTOS, that runs on the CORE-V-MCU, that allows the embedded CORE-V processor to exercise all of the IP, all of the memory, and all of the interconnect. This is also freely available on GitHub, CORE-V-MCU CLI-test. Go there, scroll down to the README, and take a look at the Quick Start Guide, and you can be up and running with CLI-test pretty much today. So that gets us to TRL3. How do we get to TRL5? Well, we want to deploy a UVM environment using a lot of the same methodologies that we employed on the CORE-V processor itself. We would apply those to the MCU. So this is an industrial grade UVM verification environment. It's fully capable of fully verifying all of the IP and all of the interconnect in the MCU. My colleague David Poulin at Datum will be talking a lot more about that. Just a little bit about the overall verification strategy. As I said before, it's system Verilog UVM. A key idea here is that we replace the CV32E40P RTL model with agents that drive the OBI interfaces. This sounds counterintuitive, but remember, we're not trying to verify the core. That's already verified. We're trying to verify the MCU. So we can drive the MCU directly from UVM sequences without having to go through the software tool chain and all the software dependencies. Of course, all of the external facing IP will be connected to interface specific UVM agents like a UART or a SPI or I2C agent. This is pretty much what you'd expect in a standard UVM environment. A nice opportunity for simplification comes from the idea that the MCU is basically a memory-driven device. So we do not need a full-up RAL model, nor do we need a full-up reference model for the MCU. We can do all of our prediction and scoreboarding at the memory level, and David Poulin will be talking a lot more about that as well. So I hope you enjoyed that quick introduction to the CORE-V-MCU and its verification. I'm now going to hand things off to my colleague, Tim Sachs, and he's going to be talking about CLI-test and the verification that's gone on to date for the CORE-V-MCU. Take it away, Tim.
Thank you, Mike, for that introduction. So I'm going to cover the CORE-V-MCU verification effort so far. Need for the CORE-V-MCU is driven by the fact, while the CV32E40P is like an exquisite V8 engine, which is beautifully constructed, carefully verified, and has massive potential, it's not particularly useful on its own. So how do we make this CV32E40P useful? Well, we start with the core itself, of course, because that's the jewel in our crown. And then we wrap that with memory and peripherals. Standard peripherals like UART, SPI, SDIO, and a chunk of RAM makes for an interesting MCU system. And then we have to wrap that with a PCB, with printed circuit board, which we call the EVK. And this printed circuit board is going to have the regulators and all the stuff needed for power. It's going to have LEDs so you can see outputs and connectors and peripherals on it. Then we're going to wrap that in the software world with a HAL and FreeRTOS, so we can exercise the CPU and run it. And then we're going to toss in, I use toss in, but actually a lot of work goes into building these compilers and so forth. We're going to toss in compilers, debugger, IDE, and FPGA development tools because it's an FPGA in the core. And now we have a useful setup that people can actually do something with. Of course, useful is in the eye of the beholder. So we need to think in terms of user types to make sure the verification meets the needs of all of our user types. So the first user type is someone who's thinking about using the CV32E40P in a project and wants to know that it isn't just a paper tiger. They want to poke and prod it. They want to exercise it, run code on it, and see that it actually performs the way they hope. The second user type is a researcher who's researching how to combine accelerators with CPUs to achieve better energy efficiency. Perhaps this is machine learning accelerators, perhaps it's other kinds of accelerators. A third user type, of which QuickLogic is one, is exploring how to combine FPGA with CPUs to improve power and performance. The FPGA might be used as an accelerator, or it might be used to customize the hardware by adding a new peripheral or something like that. And then a fourth user type is building a small system that requires a custom SoC, similar to a standard MCU, but incorporating some secret source. So this might be something like a Ring camera, for instance, or a baby monitor that has some special feature in it. And these users, the last three of these users, don't want to spend their time working on debugging the RTL for a UART or something like that. Their focus is on their special source, whether it be accelerator or some other special source. And so they want a nice working system that they can use and plug their special source into and get the data they want from the peripherals and feed that to the special source. So the verification goal is driven by those user types. Now, what we notice is that all four users want the useful setup to perform as expected. In fact, that's what they expect. And that suggests that we must exercise and verify that useful setup in exactly the same way the user will use it. And that means that we must use an app that's developed in the IDE, compile the app with the compilers in the toolset, download the app using the debugger in the toolset, run the app on the FreeRTOS, have the app use the HAL to interact with real peripherals on or connected to the PCB. Only then will that meet the expectations of a useful setup. And by the way, when we do this, we get a lot of serendipitous testing of the rest of the tools in the tool chain. So the app we built uses a command line interface package. This is a small package designed for embedded system debug. It's menu-based, so it has a hierarchical menu system. So in our app, the top level menu has a submenu per function. So if we look down the left-hand side here, we'll see a list of subunits. So we'll see miscellaneous, UART, interrupt, eFPGA, I2C master 0, I2C master 1, and so forth. Name for the submenu, and then a little help message to go along beside that. If we switch to the I2C submenu, this is I2C M0 menu, as you can see up in the left here. If we look at a screenshot, we'll see the screenshot shows what happens when you say help. So you get the name of the function, the parameters to it, I2C address, I2C register, and the little help field. And if we look at the actual command, we'll see the name of the function, the actual function name that's called, and then the the help field up here. So then if we step ahead and actually look at the code, we'll see how the CLI uses a HAL to access the peripheral. So here's the function name called out, I2C read byte, which means read 1 byte, surprisingly. Then there's the normal decorations at the top. And then here's the call to an actual HAL subroutine. A HAL subroutine in this case is UDMA I2C master read with the parameter of address, read address, number of bytes, and a buffer in which to store the result. In all cases, when this command is run, it prints out, it's a little covered up here, the value of the registry read back. So if you're doing manual debug using this to try to work out why your I2C is not working properly, you can look at that value and from that determine what's going on. However, if you're doing automated debug, you can actually provide a third hidden parameter, which is expected output. And this piece of code up here says, if I have an expected output, grab its value and set this Boolean. When the Boolean's set, the code will then check the output. And if the output matches the expected, it'll print in this message, bracket post bracket. Or if it doesn't match, it'll say bracket failed. And if something else has happened, like the command failed, it'll just say done. And then in the other option, it'll also say fail. So the purpose of these we'll get to in the next slide. So coming back to the two primary use cases for the command line interface app, first use case is during bring up or debug. So while we were developing the IP, we used the command line interface, hooked it up to a terminal, attached to the console. We typed in commands and looked at the responses, and we used this to track down errors in our code related to peripherals such as the GPIO or the UART or the I2C. We anticipate the last three types of user using it for the same reason. As they change the code around, they'll make errors and they'll want to use this CLI to help them debug those errors. The other use case is automated test. And for that use case, we have a Python program that attaches to the console. The Python program reads a list of CLI commands from the file. It issues each command and then scans the output for those keywords, failed, parsed, or done. And then it reports the number of fails divided by the number of fails plus parses. So that tells how well the regression test is working. And then it uses the done to ensure that every command actually reports a result. So a command might not report a result if, for instance, the command fails for some unanticipated reason, or if it's a new command that someone's put in and they've mistyped, say, the word failed or parsed. So done lets us check that everything is built properly and the tests are actually all working the way we expected them to. And we use this for regression testing of the IP. Runs every night, runs very quickly on the emulation. So coming back to our user types, we have different target platforms and use cases. So this whole system will run on top of a free open source software simulator called Verilator. And that's useful for software tools development. Can also run on a commercial simulator, VCS, and that's useful for timing simulation. That's helpful when you're actually getting ready to build real silicon. It runs on the Nexus FPGA board from Xilinx, which is a fast, low-cost emulation board accessible to almost everyone. And it also runs on the larger, more expensive Genesis Xilinx FPGA board. It's even faster, runs larger emulations, so people working on accelerators can put large accelerators in and emulate them. So this one's really useful for the research users. And soon there'll be the actual CORE-V-MCU-VERIF. We will use the same set of programs for EVK bring up. If we're really lucky, we'll just run the automated test and it'll all work perfectly. More likely, we'll have to do some manual mode during the debug. And then once we get everything sorted out, we can build an automated test that we can use to test each board as we build it to make sure it works end to end from the software all the way through to the peripherals. So this is the verification that we've done on the CORE-V-MCU, and it was oriented towards those first three types of users. The people who just want to use the EVK to explore the core and see if it works properly, and the researchers who are going to actually break the core and add their own code into it for bring up. What this kind of testing really doesn't do is address the full level of complexity and quality that somebody who's actually building a new SoC that they want to deploy in production use would want. And that brings us to the next step. So users planning to build a system based on the CORE-V-MCU components will want those components to be verified to the same high standards as the CV32E40P core. And that means using UVM. How that will be accomplished is the topic for the next speaker. So turning over to you, David, to carry this on. Thank you.
Hi, everyone. Today, we're going to talk about how to get the CORE-V-MCU to test readiness level 5 using a test bench based on the universal verification methodology. We're quickly going to go over the guiding principles behind the project. Why is this necessary? We're going to discuss the architecture of the test bench and the environment. So what are we building and where do things go? We're going to go over testing strategy. So how are we going to use the structure we created to generate stimulus to the duct and verify its functionality? And last but not least, we're going to go over some important implementation details. Sneak peek, it's all in the virtual sequences. So what are the project goals? As Mike mentioned, the primary driver behind this effort is to bring the CORE-V-MCU to TRL level 5 via industry standard means. So the end goal is not only a stable platform for the current RISC-V MCU, but also a powerful generic design verification and simulation environment for future RISC-V SoC designs. We're working in tandem with Xilinx to make the MCU and UVM test bench work with their free system Verilog simulator, Vivado. If you're not up to speed with Vivado, well, since about 2020, the free Webpack version can run system Verilog. So UVM, constrained random, functional coverage, code coverage, all the good stuff and features you'd expect from Big 3 simulator for free. So how are we going to achieve this? What's the strategy? Well, first off, we're building on UVM, the industry standard. Second, we're not verifying the RISC-V core within the MCU. And as a matter of fact, as Mike mentioned, we're pulling the CV32E40P core completely out of the duct. Why? Well, it's already been thoroughly verified in silicon, in silicon rather. It removes the need for a RISC-V core model, which really greatly simplifies the test bench environment and it speeds up simulation. Third, we're reusing a lot of UVM IP, much of which was already in use in the CORE-V verification efforts. So this is going to be familiar to contributors. Fourth, all DV code will be created to be compatible with the existing Open Hardware Group coding guidelines. Same as CORE-V-VERIF, it's going to be familiar to all existing contributors and users and folks in the industry in general. So let's move on to the architecture requirements. And continuing with our theme of time-tested industry standards, we're going to be using scoreboarding and self-checking tests to verify the MCU functionality. By self-checking tests, I mean we do end-of-simulation accounting. We make sure that the correct stimulus was driven and that the scoreboards observe the correct number of matches, which matches the stimulus. We're going to be expressing that stimulus via constrained random objects and measuring the overall progress via functional coverage models and their functional coverage reports. For ensuring maximum portability, we're going to capture as much business logic as possible within virtual sequences in the UVM environment. Since we're removing the RISC-V core, these sequences have complete control over resources of the MCU. Matter of fact, they implement the memory model and checker that Mike touched upon. We're reusing a lot of existing VIP in this project, many UVM protocol agents, and some libraries like the scoreboard component. I'm not going to go through these libraries today, but anyone who's worked in the CORE-V-VERIF project will be familiar with at least some of these. Most importantly, we are building on UVM version 1.2, which is still the standard today. So now that we've discussed the structure, let's go over the testing mechanics. We have 5 primary initial goals guiding our approach. We want to check functionality and connectivity from the core all the way to the I/O pads and back. We want to test that the micro DMA has been integrated into the MCU properly. We want to ensure that all peripherals are integrated correctly and accessible from the core. We want to check that the core can access all RAM and ROM locations over the open bus interface. And we want to test interrupt connectivity to the core. So how are we going to achieve this? We want a strategy that's going to tick as many boxes as possible at once. And using the DMA engine to talk to peripherals seems like the best approach. We're going to create DMA workload objects and use that to capture stimulus via UVM sequences. We're going to drive that data that we've generated to the peripherals using the micro DMA and the RAM. Then we're going to loop back that data in the test bench into the DUT. And then we wait for the interrupt that tells us to read back data from the memory, telling us that the DUT has data for us. And then finally, we read back that data from memory over the OBI interface, and we scoreboard what's written back against what was originally generated as stimulus. Make sure that everything was done properly. So here we have the full picture for simulation. So we have the DUT and its main components, the UVM test bench and the UVM environment. In this diagram, the test bench itself consists of the DUT and IO selector on the left-hand side, while the environment is everything else. The test bench encapsulates the DUT and instantiates the interfaces that are used by the agents in the environment. The agents can be thought of or grouped into 4 distinct sets. We have the RISC-V core behavioral model. Remember, we're replacing that core, so we need something to take place. That's done by 2 OBI agents, one for the memory and one for the instructions. Then we have the peripheral agents, or peripheral IO agents rather, in the left-hand side, JTAG, GPIO, I2C, SPI, etc. Then we have the interconnect agents for the APB and interrupt. These are mainly for monitoring and debugging purposes. We don't actually drive any kind of stimulus via these. And fourth, we have these support agents, clock, reset, etc. They're not actually pictured in this diagram. The environment's virtual sequencer in the top right corner of the screen is where most of the action happens. That's where we drive stimulus and provide transactions to the scoreboard. It's got some internal structure, which isn't displayed here, but most importantly, it has a DMA subsequencer. In addition, it runs multiple sequences. This is triggered by the environment, of course, during the run phase that are responsible for automating DMA operations. And we're going to touch on that and come back to this picture very shortly. Okay, so let's go over some implementation details here. Specifically, how sequences and sequence items are working together to drive all of this. The DMA sequence item is a UVM object encapsulating all the information for DMA workload. It consists of peripheral selected and an enumerated type that simply selects which end peripheral that we want to talk to, so I2C, SPI, etc. The data size, it's simply an integer that tells us the payload size measured in bytes. Payload type, so what kind of payload data pattern we want to use. We want a counting pattern, just random data, etc. And then finally, we have the data, just a byte array that consists of the payload itself. So we use the sequence item to write sequences. And this is actually what's run by the tests in the test bench. The methodology we're going with is that a test is configuration space and a virtual sequence that's run in the main phase. And we do this as much as possible. Not every test is perfect, but it allows us to have maximum portability and code reuse. Now, let me get to the virtual sequences. These are run by the environment, and they're essentially, they can be thought of as DMA software driver. We have 4 main sequences. We have setup, which, as it says, sets up the DMA engine configuration, both in memory, in the registers of the DMA itself. Send, which takes a DMA sequence item, one of the workloads that we just talked about, as an input, and writes the payload to memory, does anything else that's required, and then initiates the DMA transfer. Third, the destroy virtual sequence. This deletes the DMA queue structures from memory, and also writes some registers in DMA itself, and does some reads for statistics. Fourth, the readback virtual sequence. This is the one that waits for interrupt transactions from the interrupt agent and waits until we get the okay that DMA engine has data back for us in memory. Okay, so let's come back to that block diagram we started with and see how what we just discussed happens? What is the sequence of operations to make this happen? How does data flow from the test bench into the DUT and vice versa? First off, it's not pictured here, but during the configuration phase of the test, the setup virtual sequence configures the micro DMA and sets up any required data structures in memory. Now that's done, we can look at how a single DMA workload is performed. So first, in the top right corner of the screen, a sequence of DMA workloads is started by the test on the virtual sequencer's DMA subsequencer. Second step, the send virtual sequence takes in a DMA sequence item. The first one, second one doesn't matter, and writes that the payload that's described by the DMA sequence item to memory via the OBI agent. Then it connects the IO pads on the left-hand side to the selected target peripherals agent, the UART agent, for instance, by using pad control and the test bench's IO selector. Then we write to the micro DMA to begin data transfer and send the sequence item to the DMA scoreboard's expected port. And we're going to come back to this a bit later. So after the second step, what happens is the data is looped back by the DUT and the test bench, essentially. So data comes out left-hand side, goes to the agent, sends it back into the device. So after this has happened and the data's come back to the DMA engine and the memory, there's going to be an interrupt that's sent to the core. And of course, there's no core in this environment. So the interrupt agent is going to pick that up, and our virtual sequence, the readback virtual sequence, is going to wait for this trigger. Once it knows that it's got memory or data in memory for it, it's going to go ahead and read that data back using the OBI agent. And when it finally has that read back data, it recreates a sequence item with that data, and it sends it to the actual port of the DMA scoreboard. So now the DMA has an expected, an actual, and it can do a comparison. Fourth, the control is handed back to the DMA sequence item, running in the test. And finally, this is not pictured, in the shutdown phase, the destroy virtual sequence is going to go ahead and destroy, delete any data structures in memory, and it's going to read back any null statistics from the micro DMA for analysis further on. And there you have it. So we have to end the end-to-end testing of the MCU using the micro DMA engine and the peripherals. We really think that this is a great bang for your buck approach. It's going to get us a ton of verification done for very little work. You know, sequence items, sequencer, and a scoreboard that's off the shelf. It gets a lot done very quickly. But it is by no means the entirety of the design verification effort that's going to be required for the MCU, but it is it's a great starting point. So that's all I have for you today. I hope that it was enlightening and that you're going to check out the project moving forward. I want to thank you for your time. And do remember that this project uses all free tools. Just go ahead, download, get the code working. And we're very excited to see where it goes. We're looking forward to seeing contributions both from private companies and academia. Thank you.
Thanks, David, and thanks, Tim. That was really good, and pretty much right on the 30 minutes that I promised people. So now we'll get to the Q&A, and we have a few questions that we received beforehand. But if you have any additional questions, please don't be shy. Add them to the Q&A of this Zoom call. And I'll get the ball rolling by just asking some of the questions that we've already received. First one talks about the test plan that we currently have is based on a set of tests that C tasks that runs on top of FreeRTOS. And the question is, does this preclude the use of a bare metal environment for the MCU? And is actual bare metal use of the MCU permitted? So I'm going to hand that one off to Tim.
Okay, no, it doesn't preclude bare metal. You can certainly go ahead and do that. You get the core naked. We happen to put FreeRTOS on just because it's easier for us to use that, saves us some software work, but feel free to develop your own bare metal environment.
Excellent. Okay. So a follow-on question to that is, if users want to modify or extend the MCU, can they also download the same tests that are currently available and get started using those? And what kinds of additions would they need to do? So I'm actually going to punt that to both of you guys. So I'll ask Tim first. With the CLI environment, what would I need to do to extend the CLI test environment to support a new peripheral that I may choose to put in as my own secret sauce?
Yeah, it's a good question. And as I mentioned, we anticipated that need for other researchers. So if you add a new peripheral like an accelerator, you can definitely download the CLI. It's on the OpenHW GitHub. You can look at it. You can see how you'll add your own submenu, and then you can just follow the process. It's very easy to add new test cases in there, and it's very easy to add them into the automated test too. It was designed specifically to facilitate that.
Perfect. Okay. And David, how about the UVM environment? If a researcher or an industrial user wanted to integrate their own IP into this core, would the UVM framework that you walked us through, would it be easily extensible to handle that case?
I think so. Again, we made sure to capture all the business logic as much as possible in virtual sequences. And so it's a matter of adding to the environment, extending what exists, and modifying or extending rather the existing virtual sequences. And so from that standpoint, it should be not trivial, but we have a recipe that one can follow and continue from.
Okay, great. There's a question here that I'm going to take is, it's all around the decision that was made when the CORE-V-MCU-UVM environment was being architected to actually remove the core from the DUT and drive the core, or drive the MCU from the bus interfaces of the core. And the question is, how do we know that's not going to break anything? And really there's several ways. First of all, the current verification environment that we use, it's based on CLI test, absolutely preserves the integration of the CV32E40P. So we know that we are, well exercising the interactions between the core and the MCU, both in simulation and in the FPGA prototype. Secondly, we're not modifying anything. We're simply creating basically a shell that allows us to instantiate the system Verilog interfaces for the OBI bus. By the way, OBI is the open bus interface, and it's an AMBA-like interface that is used by most of the CORE-V CV32E40 family of cores. So we're driving that interface. So we're not actually modifying anything in there. So the fidelity of testing is preserved in that way. Remember that the goal of the CORE-V-MCU-UVM environment is not to verify the core. That's verified elsewhere. So we feel fairly confident that this is first of all, a well-worn path. We didn't invent this idea. Secondly, a very safe path, because we do, and we will continue to use the CLI testing environment, both in simulation and in an FPGA prototype. Got a couple of questions that just popped up on the Q&A. Both of them from Sergey Butran. I hope I'm pronouncing your name properly, Sergey. The first is, can I join your team and help you and share with my experience? The answer is absolutely yes. Part of the rationale behind Open Hardware TV in the first place is to promote what we are doing in Open Hardware, and to generate some excitement and hopefully generate some contributors that want to come in. So we use the term contributor. Anybody that does development for the Open Hardware Group, and that can be documentation, developing DV plans, writing RTL, writing test benches, writing virtual sequences, augmenting the CLI test. I mean, you name it. You know, there's lots and lots to do. Anybody on Earth can join. There's really two types of contributors that we engage with. The first is just members of the open source community. You know, we get this happens at least monthly. I'll get an issue raised by somebody who's not a member of the Open Hardware Group, but is curious about what we're doing, and they're asking a question, or maybe they're making a suggestion, and perhaps they actually have something to contribute. They'll issue a pull request, and we can integrate that in. The second type of contributor would be someone that would actually join the Open Hardware Group, become a member of the Open Hardware Group. I'll be blunt, this costs a little bit of money. What do you get for that? Well, you get the ability to influence the direction of what Open Hardware works on. So the reason that we have a CV32E40P core is because Open Hardware Group members decided that this was a core worth developing. The reason that we took it to TRL5 is because the members decided that it was important for the ecosystem to do that. Similarly, the reason we have a CORE-V-MCU is because the members decided that we wanted to have one of these, and the reason, you know, the reason it has the architecture that it has is because of member, you know, basically member requirements. So those are the two ways that you can join. If you are curious how to get started, send me an email. I'm at it's easy to find me, mike@openhardwaregroup.org. So there you go. So yes, you can join our team. We would love to have you. Second question from Sergey is, I have an idea about an RF MCU. How is it possible for the CORE-V with CORE-V and the RF to be implemented together? That's a bigger conversation. This absolutely is possible. One of the things that we are trying to do with the CORE-V-MCU is make it extensible. So I would recommend, you know, shoot me an email, reach out to the team at the Open Hardware Group, and we can start that discussion. So thanks for that question, Sergey. That is great. All right. All right. Just got another message from Sergey. So thanks a lot. I'm looking forward to talking to you. Some other questions. So this one would be for David. David, you mentioned that the CORE-V-MCU UVM environment works with Xilinx Vivado, which is it's not an open source simulator, but it is a free to use simulator. But does the CORE-V-MCU UVM environment work with any commercial UVM simulators such as VCS or Cadence, Exilium, or Siemens Questasim?
It's a very good question. Right now, the primary simulator is Vivado because of its availability, but we have plans to run this the test bench fluid spaces and other simulators as well. We're looking forward to community members also being able to help us out with that task. But right now, our primary simulator is Visionary. Okay,
so what would be required to get the environment to work under these other simulators? Do we actually have to change the environment, or what exactly would we update to make this happen?
Simply, if there's any kind of low level of compatibility as far as the environment and test bench have been built, we're using coding guidelines that are known to work. But there's always one thing or another that can trip off a simulator with, when you connect things up, that kind of thing. But from a UVM standpoint, it's very, very straightforward. And we know for a fact that the approach we're using, the coding guidelines and so on, work across the big VCS, NC, and so on. So we're confident from that standpoint.
Okay, so just to put a little bit more meat on that, the actual way that the CORE-V-MCU is compiled, both for synthesis and for simulation, is to use an open source tool that people in the community might be familiar with. It's called FuseSock. So we have a FuseSock core file that works with Vivado. If we wanted to get this to work with VCS, we would just need to update the FuseSoc core file and create some rules for, say, VCS or Xcelium or Questa. On the CLI environment, we actually have targets for everything except VCS. So if there's somebody in the open source community that is interested in using VCS, please check us out, and you could make a big contribution by issuing a pull request to update our FuseSoc core file to allow for the use of VCS. Cool. Okay. Some more questions. Here we go. Here's one. I like this one, and I'm not sure who to ask this one to. I think I'll try Tim. Can I load a program data into memory and run it in simulation without the cores?
You can load a program into memory. I'm not sure how you run without the cores.
Yeah, I agree with you on this.
Missing something.
Yeah. So if you're going to run a real program, you would either need an instruction set simulator model of the core or the actual core RTL itself. And I would suggest that the CV32E40P is not a very large beefy core. With Verilator, you can boot FreeRTOS and run CLI test, and the performance is very good. Definitely good enough for debugging both your hardware, the RTL, or the software. So my suggestion is, if you actually want to run a real program, instantiate the RTL for the CV32E40P into the MCU, and run it that way. Okay.
I suppose maybe if someone wants to put like a different core in there, like maybe a swerve core or something like that, you could replace the CV32E40P with a different core and run it, or perhaps put it in the FPGA and run it from there.
Sure. That's cool. Speaking of the embedded FPGA, Tim, what are we doing with regards to verification of the embedded FPGA in the CLI test? So obviously it's an FPGA. So, people say, well, what does an FPGA do? And the answer is, well, what do you want it to do? It's programmable after all. But, you obviously can't test absolutely every application that you can throw at the embedded FPGA. So how do we test the embedded FPGA in the CLI test environment?
So there are obviously various interfaces to it. So what we do is, this is always the problem in an FPGA, is we actually program a sort of test structure into the FPGA. So it might be a loopback on a data path, and then you exercise the data path to make sure the data loops around. And then for real fun, we program some accelerator into it. Our favorite one right now is part of TensorFlow Lite acceleration. And we'll run an application that runs AI that's split between the RISC-V core and the accelerator, and make sure that we get the right results.
Cool. And how about in the UVM environment, David? I assume it's a similar thing. We would put in some sort of test structure to mimic the embedded FPGA, and then run virtual sequences to just perhaps just do loopbacks to the embedded FPGA.
Yes, exactly. I think you got it right. Again, the virtual sequences is where we want to do that kind of thing, and wouldn't be very much different than what we're doing for the peripherals testing. I think what we have in place certainly extends to that very quite simply.
Okay. This next one's for you, David. Absolutely. There was a lot of talk about the UVM environment and a bunch of libraries that are part of the UVM environment, and primarily UVM agents, sequence items, things like that. Where does this all come from?
Well, if you have worked on the verification efforts for the core families. Some of those names are certainly familiar. So the scoreboard, reset agent, the clocking agent. This is agents that have been around for some time. Datum has been writing up. The documentation, the self-testing is all available as well. But these things are all been developed on their own and verified. And actually, I think on the UVM project page, we have a good listing of where to go get information about each library and how to documentation, most importantly. So it's all open source stuff for the most part, and some not open source.
Okay, fantastic. All right, I'm just looking to see if I've got any more questions here. So here's one question that came in, but I do believe it was answered in the presentation. And the question is, where is the code for the CLI test? So I can take that one. So everything that we've talked about up till now is all open source and available on GitHub. And the CORE-V-MCU itself is open source and available on GitHub. The CV32 E40P core is open source and available on GitHub. Those are in two separate repositories, by the way. So there is a CV32 E40P GitHub repository for that core. There is a CORE-V-MCU repository for the MCU that instantiates that core. The CLI test is once again in a GitHub repository, and we cleverly named it CORE-V-MCU CLI test. So if you were to Google CORE-V-MCU CLI test space GitHub, Google that, you will near the top of that list will be a link to the CLI test repository. It's once again, it's free and open source. It's up on GitHub, and it runs on top of FreeRTOS, which runs on top of the CV32 E40P in the MCU in the MCU SoC. All right. So I think we got a few more questions here, but they tend to be repeaters and of ones or variations of ones that we've already covered. And I want to be mindful of everybody's time. We're getting to the top of the hour, and although I personally love to talk about verification all day long, and I don't understand why other people don't, I do need to be mindful that people have jobs to get to and other things to work on. I'll just end with one comment. There was a comment from Sergey who sent in some questions. Sergey says, "I am a free open source software activist." I just want to set the table for expectations when working with open hardware. We support free and open source IP, the development of free and open source IP, the documentation of that, the implementation of that, and the verification of that. We are not myopic in the use of tools. So we are very comfortable using commercial tools for the work that we do. So for example, the RTL for the CV32 E40P, if you want to synthesize that into an ASIC technology, say, a 7 nanometer or even a 22 nanometer library, you're going to need to use proprietary tools to do that. And as far as open hardware is concerned, that's just fine. Also, if you're using UVM, with the exception of Avado, if you're using UVM, you're going to need a commercial system Verilog simulator. So we're, as an organization, we are not wed to the idea of everything top to bottom, front to back has to be open source. The IP we develop is open source. The documentation we develop is open source. The test benches themselves are open source, but you may need to use a proprietary technology or a proprietary tool in order to exploit these IP. So I want to make sure that that folks are clear about that. Oh, hey, there was a comment from Anonymous. I like this one. Why not use the CVA6 instead? It will also have extensions like vector and floating point. This is a good point. The CVA6, for those of you who don't know, is a member of the Open Hardware Core-V family of RISC-V cores. The CV32E40 family is targeting embedded applications for things like, you know, edge IoT, that kind of thing. The CVA6 is a true application processor that can handle, vector coprocessors. You can run Linux on this thing. It's a full-up application machine. We are actively working on an SoC platform for the CVA6. But not everybody wants one of those. A lot of people want a small embedded application for edge type, a small embedded core for edge applications. So, you know, you need the right core for the right job, and the CVA6 is, of course, the right core for a lot of jobs, but not necessarily for edge IoT. Questions keep coming. There's one here from Simon Davidman. For components in the MCU like the UART, you will have specific tests for each of the UART's modes, and will you measure the functional coverage for these? And I can definitely say yes. This is the whole idea of a TRL5 level verification environment, is we will create full-on DV plans, just as we have for the embedded cores. These will definitely, these DV plans will definitely call out all of the operating modes of these devices. And we will measure that we have verified those by using both code coverage and functional coverage. Okay, I'd better wrap it up, otherwise I am going to go past the top of the hour here. So I think I want to thank everybody for attending. You know, this has been great. I want to especially thank Tim Sachs from QuickLogic and David Poulin of Datum Technology for contributing to this. It takes a lot of time to put these slides together and to sound so smooth. And I want to thank each and every one of you for attending today, and we hope to see you at yet another episode of Open Hardware TV. And if you've got nothing to do this weekend, this is season 3. You can binge. Bye-bye, everyone. I think that's a wrap.